Okay, we are now in a stability analysis topic. Stability analysis. Okay, uh, for control systems. Okay, in these topics we learn how to determine whether or not the system is stable, right? So we have learned in the previous lectures by looking at the roots of denominator of the systems, right? Okay, simple examples of that is that, so if we have, s plus 5, this is maybe uh, whatever values here, doesn't matter, right? R of s, y of s. So what is the system stable or not stable, right? So we could determine the system stability by looking at this, right? So if we find this, we know that the roots of the denominator of the systems is -5. Then if we plot this on the imaginary axis, on the s-plane, we can find that it is on the left hand plane, and hence the system is stable, right? So okay, the same thing. The problem is that sometimes we are not able to determine the roots of denominator, especially for the complex systems, right? Let's say, for example, we have a systems like this, polynomial systems. Okay, s squared plus 3s plus 2. Okay, then we can still find it, right? Okay, there's a root is s equal to -1 and s equal to -2, right? And still stable, right? Okay, -1 and -1, sorry, and -2. Okay, still stable. Okay, what if we have a complex systems such as like this, as to the power of 5 plus 3s4 plus 2s3 plus 10s2 plus 5s plus 5. Okay, this is our system's GS. Is the system stable or not stable, right? We don't know. And then it's very difficult for us to calculate the roots, right? Even the calculator also cannot calculate, right? Even if you go to MATLAB, then you can determine whether the system is stable or not. But by hand is difficult, right? So in those days, before computer era, there was no computer. So the scientists depends on the hand calculations. Even then, they produce they invent methods to how to determine the stability of the system, right? So hence we have this stability using Rath-Hurwitz criterions. Okay, what is this criterions is that we could determine the stability of the systems using a special formula, but in this method we don't know exactly what are the roots of the systems. The important things to determine the stability is to know whether is there any positive roots. Okay, positive roots in the systems. We need to find, is there any positive roots that cause the system to be unstable, right? That is important thing to determine whether the system is stable or not, right? So if you look at this, the slide on the right, you could also download from the e-learning website. So if this case the system is stable, right? Definitely, because we can see that this all are negative roots, right? S minus 1, S minus 2, S minus 10, S minus 0. Hence, the system is stable. But how about these ones? Okay, that's not easy, right? So because we need to factor it one by one, there are a total of 5. Maybe we have more complex systems until 10th order, then it's difficult, right? So what we can do is, you know, we can use this table, okay, to determine the stability of complex systems, right? Okay, now let's go through the criterions of the Roth-Width criterion. What is the criteria? Okay, RH criterion, the first one, RH criterion guarantee that all roots in the characteristic equations are in LHP if certain sets of algebraic combinations of the coefficients have the same sign. If you don't understand, never mind, we'll go through the example, hopefully you understand, right? Second one is number of sign change in the first column of RH array equals the number of poles on RHP. Okay, if there is no sign change, the system is stable, otherwise it's unstable. Okay, how to do this, all right? Okay, let's take this example. We have a GS system with fifth order system like this, with A, B, C, D, E, and F are the coefficients of denominator of the systems. Okay, in this case, the system is in the polynomial form, right? Okay, now this is a standard, okay, a standard method to determine the stability of the system using this, the RH criterion. Okay, the first we need to build this table depending on the number of order that the system has, and then we have to fill up. Okay, now that we have that system, right? So we need to build a table. So if this system has fifth order, we just start from S to the power of 5 to the power of 4, 3, 2, 1, and 0. Okay, and then make a table like this. Okay, last one. Okay, now, okay, how to fill up? The first one, just to fill up, get the whatever values from that equation into the first top row. Okay, the first top row, the first two rows. Here, we need to fill up this. Okay, so we could also S5, this is S5, S4. Okay, the first one, the the coefficient of S to the power of 5 is A, and then B. Okay, just shift to the next one, C, D, and E. Okay, so this is 5, 4, this is S to the power of 3 here, this power of 2, this power S1, S the 0 here. So like that, right? This is 5, 3, 1, 0. Okay, so once we have this, we have to calculate the rest of the values. Okay, now come to A1 here. A1, we need to fill up this. We need to use the formula here in the table here, right, to calculate what is A1 values. So we just follow this pattern. A1 is B times E, no, B times C, sorry, B times C minus A times D divided by B. Okay, this is A1 is equal to BC minus AD divided by B. Okay, you got that. And then A2, okay, the same pattern B multiplied by E minus A multiplied by this one S1. This is F here. Sorry, just okay. BE minus AF divided by B again. Okay, that's A2. Okay, now we can calculate that. If we have all these coefficients, we got A1 and A2. Okay, done. A3, because if you calculate A3, B times 0 minus A times 0 here, that will be 0, right? So let's say this one 0, 0. So A3 is B0, A3 B0 minus A0 divided by B, so 0. So we don't consider A3. Okay, so A1, A2, that's B1. Okay, same thing, B1, it is A1, the same pattern, time D, A1, D minus B, A2 divided by A1, the same number, A1. Okay, that's B1. Okay, B2, if we have B2, okay, B2 is A1F, B2 A1, A1 F minus B 0, because it's 0 divided by A1. Okay, so you have the values B1, B2, and then followed by C1, C2, and D1. Okay, so once we fill up that, okay, we need to follow the criteria. Okay, now when we fill up this, we will come across in these three cases. Okay, the first one, we call it normal case. In normal case, when you fill up the table, you have no issue. That means all the the, the values A1 until D1 here, right, of real numbers. Can be minus or positive real numbers, but they are real numbers, not zero. Okay, they are all are non-zeros. So normal case. Okay, for a special case one, there will be a certain values of this coefficient will actually you get a 0 in one of the first column, 0, one of the row, maybe here, maybe here, maybe here, it depends. Okay, if you found this, and then the condition must follow by a non-zero or a real number next to it, then we call it special case one. The third one, special case two, there's the same condition as say special case one, but it's, the whole entire rows are zeros. Not this one is real numbers next to it, but this one the entire row zero. So there are three conditions you can see after you fill up this. Okay, most of the times we can actually solve using normal case, right? Okay, that about filling out the table. Okay, now once we have filled up that table, whatever the values of that, we need to consider only the first column. Okay, we don't really, even though we calculate these values, but the RH criteria mentions that only the first column is considered, right? Whatever values here we consider. What is that? Okay, example. Okay, for normal case, we fill up all these values. We go calculate A1, A2, B1, B2, C1, C2, and D1. Okay, we found that all these values, okay, on the first row, first column, are all positive. There's no sign change, right? There's no sign change. That means if there's no sign change, the total roots are on the negative half plane, right? So because we can see that the system is stable because there's no sign change. That's what the criterion says. All roots are on the left hand plane. have the same sign, same sign. Okay, it could be negative or positive, right? So as long as there's no sign change, the systems is stable. And then the number of, okay, in this case there are poles. Poles equal to the roots. There's another name, we call it poles. Okay, the roots, the poles. Okay, the poles, the total pole are 5 because of the fifth order systems. The number of RHP right hand planes poles 0 because there are no sign change. The poles on imaginary axis also 0. The poles on the left hand planes 5. That means that there are a total of 5. The system is stable. There's no sign change in the first row. The system is stable. That's what we want to know, right? Okay, let's see this one. The same things for normal case. We can fill up all these table, the values in this table, but then some of the values on the first column are of different sign. There's a sign change there. Let's say in this case, B1 we have negative, the rest are positive. Okay, well, we can see that. Okay, how many sign change here? How to calculate? How to count the number of sign change? You can count from the top one, A plus, right? Plus, we go to B plus. Okay, there's a number, there's 1, but no sign change. 2, root. Okay, that's 1 sign change. And then there's another 1 sign change. That's a 2 sign change, and then there's no sign change. Okay, there are 2 sign change. Immediately we know that there are 2 poles on the right hand planes. The total is 5. The right hand planes is 2. No, okay, no imaginary when poles on the imaginary axis. Okay, because this one has taken 2, this one must have another remaining 3, right? So we have 2 on the right, 3 on the left. So we can see that if we plot this, we don't know what the values are, but as long as we know there's a number, right? This, right? So there are 3 on the left, somewhere 2 on the right, but this one is just to represent the number system stable or not. So in this case 3 here, somewhere, anywhere, but 2 will be this side. Okay, the systems is unstable in this case. Okay, we stop here first. We continue to the next lecture.